thinking of here are like CMS, XBeach, Seashore, ADH, Delft 3D, Nearcom, Telemac. They're all phased average. And so that means that the governing equations, they include waves, but they include waves after they've been averaged over a wave period. So they're relegated to the world of irradiation stress, which is just a stress. It doesn't tell you anything about the details of the wave period. And so it's difficult if you don't have that if you don't have those details to include some of the important aspects of the wave shape or wave current or wave slope interaction. And we'll talk about a little bit of those. And so, for 30 years, enormous resources have gone into making nearshore sediment transport estimates for these phased average models, and yet mature process-based and calibrated nearshore morphology models have little predictive skill. And I put my own models in that category. There were some studies done a couple of years ago that showed that the leading process-based models, even when they're calibrated, they don't seem to work very well for all time. So the question is, why is this so hard? What are we missing here in these phased average models that we can improve and do better with? And so I thought we would start off by using some very simple examples where we could examine the differences that would be computed by, say, CMS or Seashore in a phased average world. And then we'll compare that with what I'm going to call a correct model, which accounts for the details of the wave shape and the wave and current interaction. Okay, so here's the rules of the game. We're gonna prescribe a free surface elevation eta that varies with space and time, and we're going to dictate that U is based on that in accordance with linear theory. So it's a progressive wave theory. So it has sort of the Koch dependence that you would expect. And the U that I'm talking about, I should have written here, is the U near the bottom. Because when it comes to sand, that's what we really care about, the velocities near the bed. We're going to also assume that bottom shear stress is quadratic with the standard formulation. So there's no phase shifting, even though we know in the boundary layer there really is phase shifting. It's 45 degrees in a laminar boundary layer. It's less so, more like pi over 8 for turbulent boundary layer. But whatever it is, we're just neglecting it all. And we're going to say that we have sediment initiation when we overcome the Shields parameter. And the Shields parameter, the critical Shields stress, tau C, is essentially like a ratio of the shear stresses that are acting on the surface of a sand grain and the restoring force, which is the gravity. And so it's typical to use a critical shear stress of about 5% when you're calculating what your sediment initiation is. And then I chose for this little example here one of the very simplest models that you can write. It's just based on the excess shear stress. This is the sediment transport, and it's a function, of course, of the grain size and the shear, and shear that's been normalized again by the weight and subtracted off once you subtract off the critical shear stress. So you have sediment initiation or sediment movement when you have tau that's greater than the critical tau. And then you'll note that if you have a large shear stress, that is that you have a tau that's much larger than the critical tau, then you have Q that goes like U to the cube. So that sometimes people call these energetic models, and they're sometimes also called U cubed models. So commonly used, and they react instantaneously to the shear stress. So this is an appropriate formulation for bed load. So we'll use this in our game today. If we take the very simplest of cases, we have transport under purely sinusoidal waves. So this is single frequency, monochromatic, pure tone, right? Linear in shape. And let's just make up some numbers. We'll say we have 1.5 meters depth and a 0.5 meter wave, 10-second wave. No currents, right? Because this is purely a sinusoidal wave. So here's the free surface. The near bottom velocity is given in accordance with progressive wave theory, progressive linear wave theory. And the shear stress by the quadratic model is the red line here. You'll note that for small velocities, you have a shear stress that doesn't exceed the critical shear stress. So you wouldn't expect to see sediment moving in those times. Only when the red line exceeds the dashed red line, which is the critical shear stress. And so here's the time variation of a sinusoidal wave of the sediment transport, which is about what you would expect, right? You might expect it to look a little bit more like a sine wave, except once you take into account the fact that you don't have sediment that moves at low shear stresses, it looks more like the last panel here. And so the actual results are in this purely sinusoidal world, no current and purely sinusoidal world, that you get, you compute zero transport. And if you look at your phased average models, seashore, for instance, then you also get zero, right? So that's satisfying in the sense that we're doing a good job with the purely sinusoidal waves. Of course, this is overly idealistic because in the real world, what you have is a combination of waves and currents. And that's what I've used. It's what I've done here. So we still have a sinusoidal waveform for the free surface position, and it's the same as the last one. But now if you look at the velocities, they're shifted down by 10 centimeters per second. And I've chosen 10 centimeters per second because that's about what an undertow would be. I think an undertow is something like 7 centimeters per second, but I just made it 10, just to make the numbers easy. So you can see that now we have a velocity profile that's a little bit attenuated at the peaks and a little bit accentuated at the troughs. Likewise, you have a more dramatic looking asymmetric wave shape for the shear stress, where the onshore stress is small and the offshore stress is much more exaggerated, and a cross-shore sediment transport that is largely offshore. So the actual results are, again, we have 10 centimeters per second as our undertow. We have a mean shear stress that's offshore, and we have a sediment transport that's about 7 times 10 to the minus 6 offshore, right? And it's offshore because I've made my current velocity directed offshore. So I think that all makes sense, right? The problem is that if we were to apply a phased average model and we use just the current part of this in order to develop the shear, that you'd end up with a result that says that it's 0 meters squared per second. So here we start to see why including the details of the phasing of the waves might be important in the overall problem. Now you could say the thing's 6 times 10 to the minus 6 sounds like a very small number, right? And it's a small number, but if you were to run that wave for about a day or two, then it would be a meter squared, about a meter squared of erosion. So we should see a meter squared of erosion, given the more realistic scenario and realistic model in this game, than if we based it on just the phased average model. So you can start to see how this unravels. And of course, the waves aren't sinusoidal. So if we look at the transport under natural waves are skewed and asymmetric. And we use the same bulk statistics. We're still in a meter, half depth, half meter wave, 10-second wave. And now I'm back to using a case where we have no currents. Then you get a skewed asymmetric waveform, skewed asymmetric near bottom velocity. But look how different this shear stress profile looks with time. You have a very, very strong onshore peak. That's moving the sand onshore. So that's the accretionary mechanism that's responsible for moving sand back onshore, which is reflected then, of course, in the sediment transport, which is mostly onshore. So the numbers are that you get 6 times 10 to the minus 6 onshore, right? In this case, with these skewed asymmetric waves. And then again, if we were to look at this, the sediment transport, we based it on solely on a phased average model, we would again compute 0. So I think those are some, at least for me, fairly compelling reasons why we would think we would have to include the details of the phasing of the waves in order to get this cross-shore sediment transport right. But another rationalization for the additional complexity that you have in this multi-scale model is that realistic bed conditions are often on a slope, right? I mean, I was talking about cross-shore transport here, and it's typical to use a slope correction term, and this comes out of river flow. So you have a corrected Q that's equal to Q on the flat ground times some slope parameter, and there's a little bit of variation in the way these slope parameters work, but they all have sort of the same form here, where tan phi is the angle, the internal friction or angle of repose, and that's about 0.5 to 0.7. And it functions in such a way that if you have flow onshore and the slope is positive, then it reduces your transport a little bit. If you have flow that's offshore and your slope is still onshore, then it accentuates that. So again, same bulk statistics, 1.5 meters, half meter wave in 10 seconds. But now I've given it a slope, and the slope's 1 on 10. So it's relatively, well, that can happen in the surf zone, right? If you look at the shear stress, there's no difference, right? It's symmetric top to the bottom because I haven't included a current in this thing. But in this case, you have an onshore transport that's this is a little bit mixed up here. You end up with there's something wrong with the sign here, but this is correct. That if you have a slope that's positive onshore, meaning you're moving from deeper water to shallow water, then you end up with an actual result that's directed offshore. And that makes a lot of sense, right? I mean, you'd expect sand to move more readily downhill than it does uphill. And then once again, if you have a phased average model that doesn't make any account for these transport, for the phasing of the transport, then you would end up with, again, a case of 0 transport, which we know isn't realistic. So that's kind of the simpler part of it, because in those cases we were just talking about, the model was formulated such that the response, meaning that the transport of the concentration reacts instantaneously to whatever's forcing it. So in that case, it could be shear or dissipation. U cubed was the example we're using, so it's dissipation. And it reacts instantaneously. And if you're talking about a very thin boundary layer, like on the order of a centimeter, that's actually very well supported by both laboratory and theoretical investigations for the bed load. Unfortunately, the world of real surf zone processes isn't quite so simple. And conventionally, nearshore transport is partitioned into a bed load and a suspended load. And so while I think we're justified in saying that the bed load reacts instantaneously to the forcing. So Q goes like U cubed almost instantaneously. It's not justifiable to say the same thing about the suspended sediment concentration. And so this is just a little cartoon to demonstrate it. So, and we'll use this nomenclature again. This is V, and V in this case stands for the volume of suspended sediment. So that is the depth integral of the concentration, the volumetric concentration. So V ends up with units of length. So you can think of it as the amount of sand, the total amount of sand that's in suspension. And then what we're really after is the transport, right? So the transport is equal to the velocity times this depth integrated sediment concentration, which can of course be split up into a steady part, that's the undertow and the steady part of the concentration, and then these tilde parts, and the tilde parts are due to the waves. So there's going to be oscillations in the flow field U tilde, of course, because it's a wavy domain. But there's also going to be oscillations in the volume of suspended sediment. So in this cartoon here we have, and this looks like it's symmetric top to bottom, but it's not actually. There's a little bit of these are slightly higher peaks, crests than we have troughs here, and the instantaneous volume of suspended sand is shown as the dashed red line. But that's not realistic either, right? Because you remember I was saying that there can be phase lags between the concentration field and the forcing, and so a more realistic look at the concentration field is given as a solid red line, and then when you multiply these two together, you get what looks like a very complex wave field, where you can have the steady part of the transport field moving offshore, and the wave related or the correlated phase locked velocities and concentrations moving onshore. Now, this isn't the kind of thing we're just going to be able to guess on, right? We don't have any way around this other than to write a model, like a simple model for this sort of transport. And so what we've been trying to do is to pick up sort of the essential physics of what's going on in this system, rather than, because there's absolutely no end to the amount of complexity that could be added to this model. I mean, you could go on and on and on. You can start talking about the depth profiles, and then you can talk about the boundary layer physics and the phase leading boundary layer physics, and then the intergranular stresses and interaction between grains. So what we're trying to do is make this as simple as we can while still maintaining the important physics of it. And the important physics of it from our perspective is the one, we get the average average concentration right, and then we get that phase locks wiggle right as well. Okay, so towards that end, we define an equilibrium concentration, and it's actually the volume of suspended sediment. And this is a page out of the Sea to Shore book, where you have the volume of suspended sediment as a function of the dissipation due to breaking. That's surface breaking, and then the dissipation due to friction. There is some small amount of that energy that's being expended in those dissipation terms that goes into suspending the sediment. This is an empirical relationship, but it's borne out reasonably well in some laboratory experiments, and it doesn't violate any intuition anyway. So that's sort of a starting point. So that would be what the dashed red line was on that previous slide. We cast the pickup, that's the amount of sand that's coming up and into the water column, so it has the correct time steady asymptote of that equilibrium volume of suspended sediment, where you have a fall velocity and then some active thickness, which is unfortunately not very well defined. In this case, we use something that's about 15 centimeters, because there's an assumption that within that first 15 centimeters is where most of your sediment transport is taking place. The fallout's a little bit easier. It's proportional to the time varying concentration. So you'll note that these look very similar, except that the pickup function has the volume in equilibrium, and the fallout function has the actual time varying concentration. And then if we just sum these, we can have a conservation statement where the evolution of the volume of suspended sediment is given by this very simple first order linear differential equation, which is nice, right? I mean, we're adding complexity to these phased average models, but adding the single first order linear differential equation is not much cost. So again, the VE, which is the equilibrium, reacts instantaneously to dissipation, and then the actual volume of suspended sediment diffuses towards it, towards that equilibrium in accordance with our evolution equation. And again, if you ask me whether or not this is correct, the answer is absolutely not. The question really shouldn't be whether it's correct or whether or not, but rather whether or not we can develop a model that has enough of the important physics in order to get useful results. The other thing that I didn't really talk about very much that is a sort of an open question is this dissipation due to breaking. We all know how the sort of Batches and Janssen models work, where you can compute what the dissipation is of breaking based on a Bohr model. But when you want to break it down to the actual phase resolved results, that breaking shouldn't occur for the entirety of that waveform, right? This is the free surface position. So we've decided to allow the dissipation to occur only for a certain portion of that phase. And that portion of the phase is when eta is above 0 and when eta dA to dt is positive. So that's the sort of the leading edge of the Bohr that Batches and Janssen based their model on. Okay, so remember I had two terms for dissipation. You have the quadratic shear stress dissipation, the bottom shear stress dissipation, and then you have the breaking dissipation. If you add them both together, then you get sort of a complex phase waveform here where you see this spike is associated with the turning on of the dissipation due to the breaking in the shaded gray region. And you have an equilibrium volume in the dashed red line, and then you have an actual concentration field that evolves by this simple first order linear equation it diffuses towards that equilibrium. Okay, and then after you have the volume of suspended sediment and you have the velocities, you can actually figure out what the transport is. Okay, so in this case, I'm using these are actual numerical results from like a simple mock-up that I'll show you here in a second. And so you have 8 centimeters per second, that in the negative direction, so that's in the offshore direction, and you end up with a suspended sediment transport that's onshore. And so it's sort of easy to understand that. It's easy to understand why the undertow or the steady current portion would be directed offshore, right? Because that's the way we dictated that our current velocity was. But then you have these phase-locked U tilde V tilde. That's the wave-related part, and it's twice the magnitude and onshore. So this is in total. Then you have something that's 6 times 10 to the minus 6 directed onshore. Even though the current alone based estimates would have you at 6 times 10 to the minus 6 offshore. So there's a substantial difference here between the what we'll call correct sediment transport and the sediment transport that's based on the phased average models. So the question of whether it's hopeless, I think, is a reasonable one. And I've come now to believe that the idea of collapsing the sediment transport closure to a general algebraic expression where we're based on the phased average model alone is actually hopeless. So Liz and I have been working on an alternative, which we're calling a multi-scale approach, where we numerically derive the closures and then reintroduce those closures back into the phased average system. So the steps in this is the menu, this recipe. The steps in this recipe are you deploy your phased average model, and from that you get your water depth, your mean free surface, your wave heights, your velocities in the longshore and crossshore direction. And you do this without any change in the model. So if, for instance, you run CMS, you would fire off CMS and start with just those averaged components as the first step in the recipe. And that is the first scale. That is the phased average scale of these models. Okay, and then we'll estimate the skewness and asymmetry because we want to have a natural waveform based on your cell number. And then we're going to invent a time series of a free stream velocity. And what I'm going to show here is all monochromatic. And maybe in the conclusions, I'll talk a little bit about the extension that we need to do to the random wave field. But in this case, we have a simple enough system of monochromatic waves where we can make just one single period of these things, and generally we split it up into something like 20 points per wave. We can estimate the instantaneous bedload transport, which is very, very similar to what I showed you earlier, so I won't go over it again. And then numerically evolve the suspended sediment concentration field based on the dissipation model, which is the slide just previous to this. Now we've got estimates of the velocities and the volumetric concentration, so we can predict transport. Once we get transport, we can move the bed in accordance with the sediment conservation statements. Okay, so I'm not going to go over this, but this is just an example of what for those interested in the semantics, this is the first scale. This is the phased average scale, and the rest of them are the phase resolving scale. So that's why we call this a multi-scale approach. So everyone should be at least somewhat familiar with this concept of a phased average model, where you have, in its simplest incarnation, you have the loss of energy flux due to the wave field by some kind of breaking dissipation. So that's an example of the prediction for the root mean square wave height that you might get out of a random wave model like Batches and Janssen. The sister set of computations is the cross-shore and longshore momentum equations. And again, I've simplified this to only its leading terms, where you have a gradient in radiation stress that's being matched by the free surface slope, or the pressure term. And you have a conservation of mass statement that dictates what your undertow velocity would be. I don't have too much time to go over these details, but Liz and I last year worked on a method of predicting what this alternately wetted and dried hydrodynamic field looks like, and in order to extend the always wet domain up and into the swash domain, which is relatively simple for these time average models, and gets to be a little bit more complex with the time domain models. Okay, so recall that we have the free surface statistics. We have things like the significant wave height, and we have the velocity statistics, and so we can estimate what the natural waveform is, the skewness and the asymmetry by Brew from 15 years ago. And so this is just an example of those predictions made, and the predictions are shown as the dashed black lines relative to some laboratory data that was taken at OSU for different in a laboratory wave flume. And you can see that while it's not perfect, it certainly seems to get a lot of the wave shape right? The things we're going to be really interested in is getting things like the peak of the crest done right, because that's so important. So this is more or less his work, and we're relatively satisfied with the way that model works relative to measured data. Okay, so if we look at this model that I laid out in a couple of slides ago, and we run it with just purely sinusoidal waves. So in this case, you would just have our cell number is equal to 0, and it collapses back to something that looks like a sinusoidal wave going to try and play a movie here. It rarely works for me, but I'm going to try it. And you can see that the suspended sediment is it's shown here in red arrows, which are pretty ugly, and the black lines show the bed load. So let's see if that works for me. Okay. So you can see we have a case where we have a free surface and a velocity through the entirety of the domain. Now it's invented, right? But it's invented to have the right statistics as the phased average model would have you have. So in that case, if we look at we're going to look at the cross-shore sediment transport. The solid red line is the suspended load, and the suspended load in this case for these sinusoidal waves is directed onshore, and that's because, first of all, we don't have a return current. In this case, remember, they're purely sinusoidal waves. And so we have the phase coupling of the cross-shore velocity and the sediment concentration, which acts to move the sand onshore. I've also shown you what the standard deviations of that cross-shore sediment transport field looks like. So the first thing to note is, first of all, the standard deviation of the transport is much, much larger than the averages, right? It's like a factor of 20 for the bed load. The bed load is, it turns out, directed offshore, and that's owing, of course, to the bed slope alone, because we don't have any asymmetry in the wave field for this case. If I do the same thing now, but now I include the return current, so that's the 10 centimeters per second that we looked at earlier in this presentation, and now there's a dramatic difference in the bed load, where we have an offshore directed bed load everywhere in the domain, and the suspended load, it's reduced some relative to the pure sinusoidal case, but it's not that much different. Okay, so now if we have a realistic wave shape with return current, and again, let's hope this works. There we go. You can even see by the arrows alone that there's a dramatic difference in the way this sediment concentration field looks. And so our cross-shore sediment transport diagram looks substantially different now. Bed load is directed both offshore and onshore, owing to the bed slope, the currents, and the nonlinear interactions. So that's a much more complicated story. And the suspended load is still directed onshore due to the phase-coupled tilde terms. Okay, so if we were to take these three cases, remember we've got three cases, one with pure sine waves, one with sine waves plus current, and one which I'm calling natural, which is a skewed asymmetric and undertow formulation. You get these three different curves, which I showed you before, but they're all in the same place here. So the sine and the current is obviously the one that's dramatically offshore. The natural has the onshore component up until about mid-surf, and then it turns to be erosive. And everywhere in these cases, we have the suspended sand that's small in magnitude but onshore. We can compute the 10-hour bed level changes by the conservation of sand statement, and we get three different curves. Now, keep in mind, it's an invented problem, right? But what you have, I think, is interesting to think about. I've taken the same statistics everywhere. This model has the same wave height here, and it has the same current here for all three of these runs. The only thing I've changed is one, purely sinusoidal waves, two, sinusoidal waves plus undertow, and three, natural waves plus undertow. And look at how dramatically different they are. First of all, and note also that there's an accumulation of sand at the bottom of the slope because the sand tends to slide down the slope here. And it's not surprising that the most erosive of these conditions, which is a simple dashed line, is the sinusoidal plus the current or the undertow. If you add back in the nonlinearity of the wave field, it acts to move some of the sand back onshore. Okay, so how about some real data? This was a good while ago where the folks at Oregon State they'd finished up a test and they were trying to move some sand, and so they decided to just run their wave maker wide open for a long time. And so this is one of the cases that I like to use when I'm writing models, because it's a huge signal, right? Here you have a retreat of something like 4 meters over 2 hours. And so I'm showing you the initial profile, which is a steep sort of dune face, and that gets eroded or eaten away with time. And the dashed lines are the model results, and the solid lines are the data. So I would say in this regard, and so, okay, and in terms of empirical parameters, there are some. I was using the Meyer-Peer-Muller defaults for the bed load. And I was using sort of the seashore defaults for the equilibrium, the volume of suspended sand in equilibrium. So there's some basis for these equilibrium, for these calibrated coefficients. So I would say that overall the magnitude's pretty good. That it, here at the top we should have something more like 3 meters, and I'm predicting 4. And also that the model is predicting the transport of sand directly offshore here, whereas the laboratory results have it spread out over a greater distance offshore. So again, I think the magnitude is reasonably well predicted, but the details are pretty marginal. Okay, so I'm not going to have much time to go over this. I'm just going to go over it super fast. But there's times when the time steady, or the time steady is too limiting. So we're working on a new simple and stable computationally efficient hydrodynamics framework that we can customize to meet USACE needs. And this is a framework that's more like the CMS model, so that it's still phase averaged, but it's low frequency resolving. And so it's based on the nonlinear shallow water equations. It's got sort of a heuristic wet and dry. I wrote a single line wave model. It really is just a single line of code. And it's in order to figure out what the time steady waves are. And then it, of course, uses the radiation stress formulation to force the domain proper. It's a little bit numerically diffusive, but it even requires additional viscosity with the supercritical flow, if you have supercritical flow. It does not include wave current interaction, and it doesn't include infragravity generation. That we could change all of that. It just gets more computationally expensive. By the finite difference solution is inelegant at best. It's first order Fisher's method in time. We go second order with pressure, except at the boundaries where things get dicey for all people. And then you use first order upwinding for the advective terms. The sediment transport is largely the same as what went on in the time steady model, where you have an instantaneous bed load and then you have a periodic suspended load. And then if you have an equilibrium transport, then you can use an explicit solution for the transport itself. If you have large spatial gradients, though, where you have difference in grain materials, or if you have instance of hard bottom, then you end up having to use an implicit solution to that. Okay, so this has a periodic boundary condition and waves. So this, you can see how simple this model is. It's not even a random wave model. I'm introducing a root mean square wave height of 1 meter here, and it shoals a bit until it breaks. And of course, when I start this little video, what you're going to see is the gradients associated with the wave height result in gradients in the radiation stress, and that will force a little bit of water up and over here. And then that water will eventually up overtop this dune. Yeah, so there you see the little bit of wave setup. Now waves are driving this filling up in here. And so that's filling up, and you can see also the equilibrium transport that's taking place as these red arrows. So one of the things that we're struggling with is how to make this swash formulation work. How to make the swash formulation work in a way that's similar enough to the time steady formulation. So I'm still sort of mulling on that one. But I have high hopes for this this new strategy. I think that it affords us the opportunity to make process-based estimates of transport, including interaction. You know, I was thinking this morning about how other models do this, like how Delft 3D does it, how BeachFX does it, and how Seashore does it. And the fact of the matter is they just totally guess. Like the one I'm, of course, most familiar with is the Seashore one, where we said that we expect to have an offshore velocity due to the undertow, and we expect to have an onshore velocity, transport. We expect to have an onshore transport due to the wave-related parts. And so what we ended up doing, and there's really no justification for this, but what we ended up doing was saying, like, take that offshore-related transport due to the undertow and cut it down by some fraction, like a half. So if we were to compute an offshore transport of 3, then we would say, oh, well, we really need an onshore transport of 1.5. So let's make it 1.5 offshore. So it's just a total guess. So at least now I think we have some justification for making these wave-related transport estimates. Same way with the bed slope, where you have this is a nonlinear process. You can't just move you can't just take the time average sediment transport and multiply it by the slope factor and get the right answer. I think it also gives us the opportunity to look at things more like a more careful estimation of what the bottom shear stress and the radiation stress is. Those are different subjects. And the next steps are going to be more comparisons with data. I'm looking for data that has a large morphology change signal in it, and I'm trying to get the lip tests that were done about 10 years ago in the Netherlands in the Delft tank. I would prefer to keep it with one-dimensional data right now rather than field data, but we'll see how that goes. And then, of course, there's this open question of what we will use when we get to real random waves. We can make the 0th moment the same, or the first moment, or the second moment. Which of these moments is most important when we make a representative wave, a representative monochromatic wave when it's trying to represent a random wave field? Okay, so that's where I stand. If there's any questions.